Okay, so let's say we have a capacitor that is charged. So we do some work, we put some charge on the capacitor plates, and then we connect it to not an inductor, but a resistor, so that we can allow the energy to exit the system. So we have a resistor with resistance R. What's the behavior of the charge on the capacitor as a function of time? Well, what's the equation obeyed by charge? Well, the equation for the circuit comes from the usual, if we integrate all the way around the loop, say we start here and we integrate the electric field all the way around, back to that point, we'll get zero. Right? This is just a reflection of the fact that electric fields diverge radially away or towards charged particles. So, but this is the net voltage around the circuit. So we need the voltage across the two elements. So from capacitance being the charge on the capacitor divided by the voltage, the capacitor, we can get the voltage across the capacitor as QC over the capacitance. And we know that if Ohm's law is obeyed, the voltage across the resistor is just current times resistance. So our circuit equation, so this equation becomes our voltage here, it's Q, just leave it as Q over C plus I times R. That should be equal to 0. But these two, again, are not independent, so we get Q over C plus dQ by dt, that's what I is, times R equals 0. Let's just emphasize that this is dQ by dt, which gets us to that. And so our equation for the circuit looks like this, and we can solve this by writing dQ over dt times R equals minus Q over C. We'll bring this to the other side. So we get a minus Q over C, but we're dividing by R, so we get minus 1 over RC times Q. And we can bring the Q's all to one side and write this as dQ over Q equals minus 1 over RC in dt. Right, so things that are associated with time are on this side, but this is just a constant, and things associated with charge are here, and so we can solve the equation. Right, this gives us the natural log of charge. That's equal to, we integrate this, so let's point out that we're doing the integrals here. We get minus T over RC plus some constant. Of course, we have the log of Q, so we need to do the inverse of this to get Q, and that's, the inverse of the log, which is the exponential. And so we do e to the log of Q, and that gets us Q, but that means we have to do the exponential of all of this, so we have e to the minus T over RC, e to the minus T over RC, plus constant, but that's the same thing as e to a constant, and so let's just write that out, e to constant. But this whole thing is just a constant, so we might as well call it something else. Let's just do e to the minus T over RC times A. A is something that doesn't depend on time, but we can figure out what A must be. At T equals 0, Q is equal to A. So A is equal to the charge on the capacitor at T equals 0. But we said that at T equals 0, we charge the capacitor. So let's just call A some Q naught. So the equation for the charge in the capacitor is Q equals Q naught, the charge at t equals 0, e to the minus t over RC. So this we notice that the charge on the capacitor, unlike in the LC circuit, doesn't oscillate with time, it decays exponentially. So if we made a plot of this as a function of time, we plot the charge Q, we start with the value Q naught, and then it just drops down exponentially.